do things to your dogs pretty well.
I just magnitude about 8 by 0.05. I didn't really care. All right, welcome back to physics, everyone. So we were looking at yesterday how to add resistors in parallel and series, and then how to find REQs and then currents and all that kind of good stuff. But the question now becomes, okay, what happens if I have more than one battery? So for example, I have this battery here and this battery here. Can I now use those things that we talked about yesterday to analyze this particular circuit? And the answer to that is, well, not exactly, right? Because if we go by what we did before, we could easily say, yes, little r and R4 are in series. We could say R1 and R2 are in series, but could we say that R3 is in parallel with R1 and R2? The answer is no, because of the presence of this battery, right? So we can say R3 is in parallel with all of this stuff here, including the battery, but not just with R1 and R2. And then same thing out here, we can say, well, R3 also is in parallel with everything down here, which includes the battery as well. So the point is, anytime I have more than one battery, all that stuff that we learned is useful, but it's not helpful in this case because I can't simply combine things together the way I would want to and say, well, these two are in series, these are in parallel, because that's not true, because it's also in parallel with the battery. So we have to come up with another way to actually be able to analyze these circuits, which is actually much more general than just combining these things in parallel and series. And this is what we call Kirchhoffs loop rules. So Kirchhoffs loop rules is a more general way of actually analyzing these circuits, which doesn't require us to actually put these things in series and parallel. Now in engineering, especially those guys who are in circuits or have taken circuits before, you guys call it, I think it's mesh theory or something like that. But it's the same kind of idea, but we'll talk about where this actually comes from. So Kirchhoffs loop rules comes down to basically the two things we have seen so far, and we talked about in lab as well in lecture, and that is what we call the loop rule, where the loop rule is just conservation of energy. Whereas we talked about what that means then is if I go through a closed loop, so for any closed loop, what has to be true is that the change in potential must be equal to 0. So through any closed loop, we have to have a change in potential as I get back to the original position at which I started at, has to be equal to 0. So this is what we call the loop rule. And the second rule is what we also talked about before, which is called the junction rule, which is just conservation of charge. Says that at any junction, what has to be true is that the sum of the currents going into the junction must be equal to the sum of the currents going out of the junction. So this is what we call the junction rule. So basically, Kirchhoff loop rules is just based off of these two things that we've already seen. We already talked about the loop rule. We use that a lot in lab. We've also done it a lot in class. Also the junction rule. But along with these two things, there comes a handful of sign conventions. So first we have to talk about the sign conventions so we can actually use this thing in a proper manner. Okay? So what are our sign conventions? Let's talk about these sign conventions. So first off, let's talk about batteries or EMFs. So for battery, we say is, okay, so here is my point A. Here is my negative terminal, here's my positive terminal, and then here's my point B. Okay. Now, if I go across the battery going from A to B, meaning we're going to go in this direction across the battery, so my change of potential is going to be the potential at B minus the potential at A. Okay, so this is my final potential minus my initial potential. Because in this case, I'm going across the battery from the negative terminal to the positive terminal. I have to increase potential, which means I'm going to increase the amount of potential by that of the battery. So the point of the battery is simply to add potential. So this is going to be a positive increase in potential. If I went the other way, if instead I went from B down to A, so in this case, my change of potential would be the potential at A minus the potential at B. In this case, I have to drop by an amount of the potential of the battery. Because on this side at B, I have a greater potential than I have at A. So in this case, I have to decrease by an amount of the potential of the battery, which again is what we simply call our EMF. So this is for batteries. What about for resistors? So for resistors, again, let's say this is my point A, this is my point B. here is my resistor. So this has resistance of R. Now for resistors, it's a little more complicated because now it depends on the direction of the current. So let's say for funsies, my current is actually going in this direction. So my current is going from A to B. Now, if we go across the resistor, looking at the resistor in the same direction as the current, meaning we start at A and then we go to B, what has to be true is that the point of a resistor is to lose potential, which means that the potential at A has to be greater than the potential at B, which means I have to decrease by an amount of Ohm's law. Right? So in this case, if I go across my resistor in the same direction as that of current, my change in potential, because my potential at B minus the potential at A must be equal to negative the current times the resistance by Ohm's law. Okay, I have to decrease. I have to have a lower potential here than I had that here. Now, if I go in the opposite direction, meaning if I go this way across the resistor, so in this case, I'm going across the resistor from B to A. In that case, again, since B is lower than A, then I have to increase by an amount of Ohm's law. So in this case, my potential difference, A minus the potential of B, is then a positive I times Ohm. So in this case, just simply saying the potential here is less than the potential here, which means I have a potential step up going across the resistor when I go in the opposite direction as the current. So again, if I go in the same direction as the current, I have to lose potential. If I go in the opposite direction as the current, I have to gain potential. So this one, it depends on the direction in which the current is going, as well as the direction at which we go across it. You'll see what that means in just a second. The last one then is capacitors. That's the only other thing that we've looked at. So let's look at capacitors. So for capacitors, again, I have A here. I then have my parallel plate capacitors, or just whatever the capacitor is. Point B, and let's say this is our positively charged plate. And this then is our negatively charged plate. So in this case, if I go across the capacitor from the positive charge to the negative charge, in this case, then I have to drop potential. So my potential difference at B minus potential at A, and then it has to be equal to negative Q divided by C, because remember, Q is equal to C times B. So in this case, my change of potential is going to decrease going from the positive side to the negative side. If I go the opposite direction, go from negative to positive, in this case, we have to gain potential. So my potential at A minus potential at B then must be equal to a positive Q divided by C. In this case, if we go the opposite direction, then that means my potential here is lower than the potential here. So I'm stepping up, I'm increasing the amount of potential by the charge about the capacitance. Okay, what's up there?
Why is VBA going in the direction of A?
Because remember, when I write this, what I really mean is, write it this way. So VBA is the same thing as the potential at B minus the potential at A. Okay. So this notation means potential at B minus potential at A. So I'm saying here that potential here is less than the potential here, which is what gives me the negative. Okay. So Kirchhoff's loop rules and the way we analyze these particular circuits comes down to, again, just the loop rule, saying anytime I go through a closed loop and I go back to the initial position in which I started going through that closed loop, my change of potential has to be equal to 0. And the junction rule, which says that at any junction, the amount of current which comes in has to be equal to the amount of current going out, plus these 3 different sign conventions. These things together allows us now to analyze any particular circuit that we actually want to take a look at. So how does this actually work? So let me draw that circuit we had in the beginning. Let's kind of look at this example here. So again, I had my battery down here. So this is what we call E1, connected in series with an internal resistance, little r, connected in series to R4. This guy then was connected here with R1, connected then in series with R2, connected in series with a battery pointing in the opposite direction as the original battery. All connected then in parallel to simply R1. Okay. So let's talk about how this actually works. So how this works is you're going to be given something like this, where this something is going to have simply numbers for all of these different objects. So for example, I'm going to tell you what E1 is, I'm going to tell you what R, R4, E2, R1, R2, and R3, and that's it. And I'm going to ask you questions like, what's the current through the system? So the first thing we have to do then is what? First, identify how many independent the number of loops that we have. So what does that mean? So here I technically have 3 loops, right? If I start at this position, I go through, I can go through this closed loop here. So that's closed loop number 1. I could go through in this direction, which is closed loop number 2, or I could go around the outside perimeter, which would then be closed loop number 3. So in this case, I have technically 3 loops. But how many independent loops do I have? So what I care about is the total number of independent loops, not the total number of loops. Now in this case, since I have 3 total loops, I only have technically 2 independent loops. So what does that mean? That means that the big loop here across the perimeter is simply this loop here plus this loop added on top of each other. So these are linearly independent solutions. Have any had linear algebra before? I think no. Okay, great. That's fine. So basically, it just means that if I have these guys, this big loop is a linear solution of this loop plus this loop added together. This is all this means. So if you think about this in an algebraic expression, what I have are 3 equations, but only 2 of them are independent. The third one is based off of those other 2 pre-existing ones. It's simply a superposition of those 2 other expressions added together. So the general rule is that if I have n number of loops, only n minus 1 number of those loops are actually independent. So first of all, when we look at loops, in general, we have n minus 1 independent loops. Meaning that in this case, since I have 3 loops, only 2 of them are actually independent. So in this case, n would be equal to 3, which means we have n minus 1, which is equal to 2 independent number of loops. So what that means then is I'm going to choose 2 of these particular loops. Because again, the third loop is simply a linear combination of the other 2. Now, whichever 2 loops that I choose, it doesn't matter. I'm just going to choose 2 loops that I'm going to analyze. We'll set that up in just a second. The other thing is the junction rule. So notice here I have 2 junctions. I have 1 junction here and I have 1 junction here. And what the junction rule says is that all the current coming into here has to equal the current coming out of here. But simultaneously on this side, it also says that all the current coming into this junction is going to be equal to the current going out of this junction. Now notice here, if I start at this position and I go across the top portion here, all of this has 1 current. From this position to this position, all of this also has 1 current. And starting here, going around through this position, all of this also has 1 current. Which means in general, I have 3 currents in this position, in this problem. 1 current through the top leg, 1 current through the middle leg, and 1 current through the bottom leg. Now, if I look at this junction versus this junction, the 2 junctions are going to tell me the same information. So for example, if I say, oh, here I have current 1 going in this direction, current 2 going in this direction, current 3 going in this direction. At this junction, it says current 1 and current 2 are coming in, but current 3 is leaving. On this side, it says current 3 is coming in, but current 1 and current 2 are leaving. Those 2 expressions are exactly the same. They're just reversed from each other. Which means also when it comes to junctions, in general, if I have n number of junctions, I have n minus 1 independent number of junctions, because the 2 junctions give me redundant information. So when it comes to junctions, again, we have n minus 1 independent junctions. The information is redundant. So in this case, if I have this junction here, let's call that junction A. This one I have junction here, let's call that junction B. All this means then is that if I use junction rule A, I don't have to use junction B as well because they give me exactly the same information. It's redundant information. So what does this mean? So what this means is that basically what we're going to do is since I have 3 currents, I have 1 current which goes to the top leg, 1 current which goes to the bottom leg, or sorry, middle leg, 1 current that goes to the bottom leg, I then have 3 currents. So what I'm going to ask you is basically what are those 3 currents? So since I have 3 loops, only 2 of them are independent, which means I'm going to use 2 equations from the loop rule. From the junction rule, I have 2 junctions, but I'm only going to use 1 of them because the other one is, again, redundant, which means that gives me a 3rd equation. So I'm going to have 3 equations for 3 unknowns. Okay, there we go. how many equations do I need to solve for 3 unknowns? 3, right? So what loop rule does, or Kirchhoff's loop rule does, is it allows us to then be able to come up with algebraic expressions for the total number of loops or the total number of currents that we need to solve for. This is what Kirchhoff's loop rule does. So again, here we're going to apply the loop rule on the top one, the bottom one, or say the top one and then the big one, or the bottom one, the big one, doesn't really matter, whatever it is that we choose. And then we're going to use the junction rule. From there, we'll get 3 equations. We'll have 3 unknowns to solve for. We'll solve for those 3 unknowns. Life will be changed. All of this just comes off of the loop rule, the junction rule, and those handful of sum conventions. So how does this work? So let's write down some steps. So step number 1 is we're going to label all currents. So what does that mean? We're going to write down the directions and magnitudes of the currents. Now, what does that mean? So what this means then is we are going to simply, on each one of these legs, choose a current and choose a direction from that current. Now, why do I have to care about the direction since current doesn't have a direction? Remember, it's a scalar quantity. Well, I have to use a direction because of these sign rules. So I have to know the direction in which the current is moving to assign if it's going to be a positive increase in potential or a negative potential drop. Right? So I have to assign the direction of a current. Now, does it matter the direction of the current that I choose? The answer is no. Just like when we did forces, way back when we did the sum of the forces, Newton's second law, and we said we had something like an inclined plane, and one of them was going to accelerate up, one was going to accelerate down, or one was going to accelerate down, the other one's going to accelerate up. We said the direction of the acceleration didn't matter because the magnitude ends up becoming the same anyways. The only thing that's going to happen at the end of the day is our acceleration would become either negative or positive, telling us we chose either the correct or the wrong direction of the acceleration. Right? So again, if we think about going back here, here's my inclined plane. There's box number M1 here, box number M2 here. These guys were connected together. If I said my acceleration was going in this direction, so this guy was accelerating downward, and it turned out it actually went in the opposite direction. Acceleration was this way, and this one was accelerating up. At most, what would happen is our Newton's second law would give us a negative acceleration, but the magnitude would be correct. Here, it's the same thing. As long as I choose the direction of my current, doesn't matter if I choose the correct one or not, because at the end of the day, all I'm going to get is a negative sign. But the magnitude will be the correct amount of current. Okay with this? So the first thing we have to do then is decide and label currents in their directions. So that magnitude and directions. Now, let's practice that. So again, I have 3 currents. That's from this junction. I can have current run through from here to here. All this has to be the same current. From this junction, I have current, say, running in this direction. So all this has to be the same current. And then from here, all the current has to be running the same throughout this leg. So again, I have 3 currents. All we then have to decide is which one is I1, which one's I2, and which one's I3, and what's the direction that they're running. Now, again, how you want to do that is completely up to you. It doesn't matter. It's completely arbitrary. But typically what I do is I look at the direction of the battery. Because what I know is that current has to be leaving from the positive terminal, eventually come back in through the negative terminal. So in this case, what I would say is, well, this current is running in this direction. This current is running in this direction. And then for this current up here, all it has to do then is satisfy the junction rule at the 2 junctions. Which means I now have either a choice or no choice, depending on how the direction I took those currents. But do I have to do that? Again, no. Doesn't matter. All that matters is I choose a direction, and then I have to make sure it satisfies the junction rule. So, Omar, I'll pick on you first. Which leg you want to look at? Top, middle, bottom?
Middle.
Middle, great. So which direction you want the current to be going? You want it to go that way or that way? Again, doesn't matter.
Left.
This way?
Sure.
That's my left. So your left or my left?
Your left.
Okay, so this direction. Good. What current do you want to call that? So we want to go this way. You want that to be I1, I2, or I3?
I2.
I2, right. So we're gonna say I2 then is moving in this direction. It's okay? Bruce, I'm gonna pick on you now. So you got two choices. You want the top leg or the bottom leg? Bottom leg, great. So you want it to be going to your right or your left?
Right.
Right, great. So we're gonna have it down here. So it's gonna be I, and you want this to be I1, I2, or I3? I1, great. So we have I1 going this way. And finally, Jessica, I'm gonna pick on you. So you get the top one. That's all you get. Okay? Now, in this case, you actually don't get a choice. So tell me why. Good. So in this case, what's the direction of this current? Is this going into this junction or out of this junction? Into. What about this one? Is it going into or out of? Into. So if I have two currents going into, can I have this current going into? No. So in this case, I have to satisfy the junction rule, which means that I have to have some current coming out, which means Jessica, fortunately, Padres gave you no choice. You're going. So let's call that hard. All right. What's up?
So if I1 and I2 are going in opposite directions, we would still be able to pick the direction of I2.
Correct. So if Omar picked I2 going this way instead, for example, then I would have what's I1 coming in, I2 leaving, and then Jessica could have chose anything that she wanted to, either coming in or going out, because it has to satisfy the junction rule. But as long as I already have some coming out, she can choose any direction that she wanted to. But in this case, these guys both chose them to going into the junction, so the only other possible choice we can have in this case was forced on us. It had to be going away from the junction. Good. So this is step number one. So step number one, we're going to identify how many unknown currents I have, which in this case I have 3. We're then going to label them magnitude-wise, which is I1, I2, and I3, as long as the directions as well. Okay. What's then step number 2? So step number 2 is then identify independent loops. So what does that mean? So again, that means, and here I have 3 loops. Again, I have the big one, I have the 2 small ones, I have the top one and the bottom one, which gives me a 3 number loops. So here, your job then is to now just decide which one of these loops am I going to go over? Because I have to apply the loop rule to a closed loop, which means, am I going to use the big one and a small one, the big one and the other small one, or 2 small ones? Now again, it doesn't matter, but I just have to make a choice. So which loops you want to use? So Tara, give me a loop. So you want to use the big one, the top one, or the big one, the bottom one, or the small ones? Just choose one.
Just one.
Just one.
Big one.
The big one. Okay. So here I'm going to say, well, this is going to be my loop number 1. So loop number 1, I'm going to use the big one on the outside. Cesar, what's the other one that you want to use? You want to use the top one or the bottom? The bottom one, great. So I'm going to say this is my loop number 2 that I'm going to go through. So in this case, I'm going to use the big one and I'm going to use the small. Okay. Step number 3, choose a direction to go around the loop. What does that mean? So that means when I'm going around my loop and I'm applying my loop rule, so if I'm using the big one here, the question is, am I going to go through my loop in, say, counterclockwise direction? Or am I going to go around my loop in the other direction, which is the clockwise direction? Does it matter? Of course not. But it does choose what all the different signs are going to be. Right? So Derek, for the big one, you want to go in the clockwise direction or the counterclockwise direction? Counterclockwise direction. Good. So in this case, we're going to go in the counterclockwise direction because that's the direction of the currents. Always a good choice. Let's follow the directions of the currents. Okay. So for this one, we're going to go in this direction. Okay. So now we're just going to make a direction in which we're going to go. Who's up next? So the lines are kind of tilted. So Brooke, loop number 2, do you want to go in a clockwise or counterclockwise direction? Counterclockwise again? Okay. So we're going to go in this direction around this. Now, in this case, this is a good example where here, down here, we're going in the direction of the currents, but up here, we're going to go in the opposite direction of the current. So we'll see what the difference is as we actually do those things. Good. What's step number 4? Step number 4 then is we're going to identify and choose an independent junction. So in this case, since we only have 2 junctions, we're going to choose which junction we're going to use. Again, since we have redundant information, doesn't matter which one we choose, it gives us the same expression. But let's go ahead and choose one of them. So who's up? So we're back there. So Paige, which junction you want to use? Do you want to use junction A or junction B?
Junction A.
Junction A, great. So in this case, we're going to use simply junction A. Step number 5, apply the loop rule. So now that we've made our choices, we're now going to simply use our choices and start applying the loop rule. So what that means then is for the loop rule, we're going to go around the big loop in the counterclockwise direction, applying all of our sign rules as we go through this. Okay? Now for here, we're going to make a choice on where we're going to start, because we have to start at the points and then go around and then end at that same point. So we know we ended up at the same point. Otherwise, it's not equal to 0. Now, typically what I do is I start off at a junction. So that way when I go around, I come back to that junction, I know I reached my final point. But again, it's up to you. It doesn't matter. You can start in a corner. You can start anywhere that you want to. But I'm typically going to start at a junction. So let's go ahead and do that. So let's start at a junction. So I'm going to start at A. And we're going to go around in this direction, because that was the direction that I was told to go. So let's do that. So I'm going to start here. First thing I'm going to run into is the battery. I'm going to go across the battery from the negative terminal to the positive terminal. So is that a positive increase in potential or a negative decrease in potential? Positive increase in potential. So here, I'm going to go back to here, looking at loop number 1. First thing I run into is a positive EMF. Next thing I run into is R, where R has I1 going through it, and I'm going across the resistor in the same direction as the current. So is that a positive increase in potential or a negative drop in potential? It's a decrease in potential. So in this case, I'm going to get a minus I1 little r. Next, I keep going. Next thing I run into is R4, which has I1 going through it. I'm going across the resistor in the same direction as the current. So is that positive or negative? Negative. Good. So I'm going to get a negative I1R4. Next thing I come into, so I'm going to bypass the junction, go off to the top. I'm going to run into this resistor. I'm going to go across the resistor in the same direction as I3, which means that positive or negative? Negative. So I'm going to get a negative I3R1. And now finally, I come all the way back to the junction. So I'm at my starting position, which means this all now has to be equal to 0. So that's my first loop. So it's okay? Not too bad. Now let's look at loop number 2. So loop number 2, again, we're going to go through this bottom one. And we're going to go in, again, the counterclockwise direction. So I'm going to start off at the same point. I'm going to start off at junction A. Do the same thing again. I'm going to go through junction A, come down through here. First thing I run into is the battery. I'm going from the negative to the positive. So is that positive or negative? Positive. Next thing I run into is the current through R. I'm going in the same direction as the current. So is that positive or negative? Negative. Next thing I run into is R4. I'm going to go across R4 in the same direction as the current. So is that positive or negative? Negative. Good. So let's write all that in. So for loop number 2, I'm going to get an E1 minus I1R minus I1R4, the same thing as before. Okay. But now, at the junction B, instead of going up, I'm now going to go in this direction, because now I have to go through the middle one. So now I'm going to go across battery E2 from the negative terminal to the positive terminal. So is that positive or negative? So from the positive to the negative, or sorry, from the negative to the positive. Is that positive or negative? Positive, right? So So in this case, I'm going across the battery from the negative terminal to the positive terminal, so I have to increase in potential. Next thing I run into now is R2, which has I2 with the current running through it, but I'm going in the opposite direction as the current. So if I go in the opposite direction as the current, is that a positive increase or a negative decrease? Positive increase. So in this case, I'm going to get a plus I2 R2. Finally, I'm going to keep going. I'm going to go through R1, which has I2 running through it. But again, I'm going in the opposite direction as the current. So is that going to be positive or negative?
Positive.
Positive again. So then I get a plus. Plus I2 R1. And now I'm back to the junction. So all that then has to be equal to 0. What's up there?
So the battery doesn't matter what direction the current is, it only matters what direction you're going through.
Correct. Yes. Yeah. So if we go back to our rules here. Exactly. So here we never made mention of the current. We only made mention of how we go across the battery. Exactly. So as long as I go from the battery from the negative to the positive, it has to be positive. If I go from the positive to the negative, it has to be negative. Now, what is going to be different though, we'll talk more about this as we kind of get there. What'll be different is the battery discharging or is it charging? So the way that Omar has this set up with current going into E2, what that means is that E2 would actually be charging. So I would be using, in this case, E1 to charge E2. So if my current is going in this direction, which is going into the positive instead of away from the positive, that means the battery is being charged, not discharged. For this one, since the current is moving away from the battery, that means the battery is being discharged. Right? Does that kind of make sense? So the direction of the current does dictate what the battery is doing, meaning am I charging the battery or am I using the battery to run the circuit? So once I actually decide, or when I come up with my numbers here, then what will happen then is I'm going to find out if this is positive or negative. So if this ends up being positive, what that means is I am charging this battery, but if it turns out being negative, it means going in the opposite direction, which ends up discharging. So exactly. So the current actually doesn't matter for the battery increasing potential across it or decreasing, but it does matter if the battery is being charged or discharged. That makes sense? So what?
Do we have two resistors named R1?
Do I have to leave R1?
Isn't R1 in loop 2, but it's in
It's the
Oh yeah, that should be R3. Which one was R3? The top one was R3. Sorry about that. That should be R3. So that means that this one was actually R3. Good. Okay. What's up, Omar?
And you can always remove one of those equations and then count the top. Right?
Yeah, so instead we could have done the top one, which then we would still have two equations, but they would just be two different equations. So yes, perfect. So finally, step number 6, we're going to apply the junction rule. So Paige told us we're going to look at junction A. So according to our diagram, what's coming into junction A and what is leaving junction A? So Dalton, what's coming into junction A? I3, and I3 by itself, right? So in this case, I would then say, well, I3 then at junction A is then equal to, because that's the only current coming in, must be equal to the currents coming out. But what currents are coming out according to A? Well, 1 and 2, right? So I have current 1 coming out, current 2 coming out. So in this case, my junction rule simply says that I3 must be equal to the sum of I1 plus I2. Okay. Finally, step number 7. So this is Kirchhoff's rules. Now, the point about using Kirchhoff's rules again is that as long as I follow this process and I identify everything and I choose directions and I'm consistent with those directions, I will never ever get the wrong answer. At most, what I'll get is a negative current instead of a positive current, which simply means that I chose the wrong direction. What does that matter? No. So let's put some hardcore numbers onto this and see how this actually works. So let's say that in this case, E1 was equal to 8 volts. E2 was equal to 45 volts. R1 was equal to 1 ohm, that's my internal resistance. R1 is equal to 40 ohms. R2 then was equal to little r, which was equal to 1 ohm. R3 was equal to 30 ohms. And finally, R4 was then equal to 20 ohms. Now, your job at this stage then is to solve these 3 equations simultaneously. So this is your job at this stage. Now, however you want to do that is completely up to you. There are, of course, millions of different ways you can solve simultaneous equations. But in this case, I'm going to just tell you what our answers turn out to be using the equations that we have. Make sure I get all this correct. There's mine. Oh, there it is. Okay. Which way I chose these things. Okay, so what I said was, go back to my pictures. So I3 we had going that way. So in this case, I would find that I3 was equal to, that was equal then to a positive 0.86 amps. So we chose the right direction. I2 then was equal to, which was I2, the bottom one, same as ours, same direction. So we found that as 2.58 amps. And then finally, I3, we said was I1, was actually then equal to a negative 1.73 amps, which means we chose the wrong direction. So how do we do these? So the easiest way to do this is to use a method. I'm going to kind of teach you a little bit of linear algebra, but I'm not going to fully teach you linear algebra, which is the fastest method to actually solve these things. Now, I'm going to show you how to set these up, and then I'm going to send you on your way to then watch YouTube videos to try to figure out how to actually do this on your calculator, because it's a series of like 3 buttons, and your calculator will do all of this for you. It's going to save you like 20 minutes worth of algebra on the AT. It's going to be great. Okay. What you're going to use is something which is known as row reduced echelon form. So you're looking for this guy. It stands for row reduced echelon. This uses what's known as an augmented matrix. So what's an augmented matrix? So basically, an augmented matrix, we're going to use those equations to create what's known as a matrix. Okay. So let me just go back and let's recopy our equations here just so we know what they are. Okay, so our first equation was that we had an E1 minus then an I1, was it? R, minus I1 R4 minus I3 R3 is equal to 0. And then our second equation was I1 minus I1R minus I2R4 minus I3R3 plus E2 plus I2R2 plus I2R1 was equal to 0. And then finally, our junction said that we had I3 was equal to I1 plus I2. Okay. Now, what we're going to do is we're going to use these 3 equations to rewrite them in a way that we have all the currents on one side and then all of the non-currents on the other side. Okay. So what does that mean? So it means I'm going to simply rewrite this expression to get all the currents onto one side. So I'm going to take this expression and add them all to this side, which means I'm going to rewrite this expression as I1 times R plus R4 plus I3 R3 is equal to E1. Okay with this? What's up, John?
Where'd you get the I3 R? The second.
Didn't we have that before? Right there.
The second.
Second equation? Did I write that down? Oh. Sorry. Good. I got a little overzealous. What's up?
Also, isn't that supposed to be I1 R4? Second equation.
Yeah, but I'm factoring out the R1. That's why it's in parentheses.
So the second one, you have I2 on four.
Oh, yes. Sorry. I think I said R1, but anyways, yes. Okay, so now I'm going to do the same thing over here. So I'm going to move all the currents to one side and anything that's not a current to the other side, which means in this case, I'm going to rewrite this then as, let's rewrite this. Thank you. So it's going to be an I1, again, R plus R4, minus then, I'm going to get a I2, R1 plus R2, is all then equal to E1 plus E2. This current here is negative, of course, because we brought it to the other side. And then finally, for down here, I'm simply going to move this guy to the other side. So I'm going to get a 0 is equal to I1 plus I2 minus I3. Over here, we're going to get a 0 is equal to I1 plus I2 minus I. Okay? So the way that this works is we're going to create what's known as an augmented matrix. Now, what this means then is we're going to create a matrix where the first column of the matrix is going to represent all of the stuff which is multiplied by I1. The second column is going to represent anything multiplied by I2. The third column is going to represent anything multiplied by I3. And then the augmented part is going to be the answer. Okay? So basically, all I'm going to do is go back to each one of my equations and then read off what is multiplied by each thing. Which means in this case, I1 has R plus R4. So that means under here, all I'm going to do is I'm going to write R plus R4. Okay? That's my first element. Looking at my equation again, I have nothing multiplied by I2, which means what's the coefficient for I2? 0. So then in that one, I'm going to write simply 0. Then I'm going to write the coefficient for I3, which was simply R3. And then this was all equal to E1. Okay, so this is going to be my first row of my augmented matrix. Well, the second one, I'm going to do the same thing. So again, I'm going to have an R plus R4 for I1. I2, I then have a negative R1 plus R2. We'll write that down. Here I'm going to get a negative R1 plus R2. Wrong direction. There was no I3 here, which means again, my coefficient is going to be equal to 0. The answer was then E1 plus E2. And then for the last one, then I get a 1, a 1, a minus 1, and a 0. Remember, I had I1 plus I2 minus I3 was equal to 0. So this is what's called the augmented matrix. So all you're going to do is you're going to insert these coefficients just like this into your calculator. Now, you're going to hit a few buttons. And what your calculator is going to spit out is something that looks like this. 1, 0, 0, 0, 1, 0, 0, 0, 1 with answers. Now, in this case, our answers are going to be these answers. So I'm going to get a negative 1.73, 2.7 something. Oh, sorry, 2.58. And then finally a 0.86. So your calculator is going to do this number crunching for you. So you have the negative 1.73, 2.58, and then 0.86. And what it says then is that I1 is simply equal to this number. I2 is equal to this number, and then I3 is equal to this number. Right? So your calculator is going to do all the algebra for you to get you to the answers, and all you need to do is learn how to do it. About 5 minutes. What's up, Omar?
I1 plus I2. That's equal I3.
Well, yeah, so remember I brought that term to the other side because I want anything that's not a current on one side. So that's why for this one here, again, I have now 0 is equal to the I1 plus I2 minus I3, because that's the same expression.
Did that know if you added 0.86?
What are you saying? Okay, so you're saying one of my signs is not correct?
Sorry, what was it?
All right, let me check my numbers here. Got all my stuff back. Quick check. So I had I3 on now. So this is negative. I3. Oh, you're right. I wrote that wrong. So I3. No, so I3 is positive 6. So then I3. Oh, I see what I did. So I2. Sorry. These two were switched. This should be. So that was 0.86. That was right. This was then 1.73, and then this was a negative 2.58. Sorry. I used different notation in my notes, and that's why I got. Sorry about that. Yeah. So now if I add all three of these together, now I do get 0. Okay. Good. Sorry about that. So this is what we call, again, row reduced echelon form. This is the easiest and fastest way to actually be able to solve these different forms. What's up?
What happens when we have more than 3?
Oh, that's fine. Then you just set up another row. And then in that case, you'll have, instead of 3 equations with 3 unknowns, you would have 4 equations with 4 unknowns, or 5 equations with 5 unknowns, and et cetera. So you just do the same thing. So you would then have a column for I1, column for I2, column for I3, column for I4, column for I5, column for I6, et cetera. And then you would just augment that in that particular direction. What up?
Can these kind of calculators?
I don't think so, but maybe. But I know the graphic calculator is definitely different. Otherwise, if you don't have a calculator that does that, then you would just use your usual methods for solving these things. So for example, you would just use this equation, for example. Let's see, so this one has an I1, this one has an I2, this one has an I1, this one has an I3. So in this case, what you do is you would solve this equation for I3 in terms of I1, solve this equation for I2 in terms of I1, plug that back into this expression. So then I3 would be in terms of I1, I2 would be in terms of I1. So now you have one equation which is only in terms of I1. Solve for I1, from there, plug that back into those other expressions, and then find I2 and I3. More algebra, but. So tomorrow, we'll set up a few more, we'll get some more practice on how to actually do the loop rule, the junction rule, just so we know exactly how this thing works. And then from there, we'll talk about the last part of this chapter, which is RC circuits.
We have to solve for resistances.
I'm sorry?
We already asked to solve for
You could, so for example, I could give you one of the currents and not the other 2 currents, and then ask you, for example, what's the, and then not one of the resistors, and then ask you what's the 2 currents in the resistor. So as long as I have any 3 unknowns.
So we're going to be able to use the matrix solver.
Yeah.
But you just prove your resistance as its own.
Correct, so it would just be its own column.
Okay.
So in that case, if I had something like that, then I would have, for example, I1, I2, R1, and then answer it over.
Okay.
So I would just set up something like that instead. Yeah, but you can still use the matrix. You just have to know what each one of the different columns is. That would be okay.
Like you have a numerical.
I did, let's see here. So probably Friday would be the best. It looks like you're busy tonight, right?
I have to work. Right. I was hot to blue brown, so eight, but and almost.
Oh, okay.
I have to see it from 8 to 8:30.
Okay. Well, then I'm getting all my kids to bed, so. But and that's fine. So, yeah, we could probably do earlier. Otherwise, Friday, because Thursdays are not gonna work. Yeah, so. Okay. Got it. Yes, we could do today if you want to do today. Otherwise, then Friday would probably be best. Okay, so you said tonight would be fine as long as it's before.
Or after.
Oh, after 6:30.
No, 8.
8:30. Okay. That's what I thought. Okay. You could probably do that. Now let me talk to my wife and then I'll send you back. Okay. See you, Ruth.
Like cornhole, like, your money.
Well, you're presuming I have money, which is not.